All right. And here are our responses. Okay. All right. So one of them is the correct answer. I think right now we have selected almost all the answers. So in about 10 minutes, okay, we will learn how to, do this without any ambiguity. That's going to be the goal. Okay. So before we do that, I want to go back to the beginning of my slide deck. Okay. So we know, based on what we have discussed in Unit 2, Module 2, okay, the chemistry happens using the valence shell electrons. Okay. As a result of that, even when we write the electron configurations, we write the core shell with a noble gas configuration or a noble gas notation, and then write out the valence shell electron configuration because that is what is important for us. Okay. And then we also noticed in the valence shell, we usually have 8 electrons. We can have up to 8 electrons in the valence shell. Okay. But if you don't have 8 electrons, meaning if we have vacancies, and those vacancies determines the number of bonds they make. Okay. For example, if you take a molecule, atom like fluorine, chlorine, bromine, they have 7 electrons in the valence shell, meaning they have one vacancy, because they can have up to 8, they only have 7, therefore they have one vacancy, therefore they're going to form one bond usually. That's their common bonding pattern as well. Now there is a rule. I don't know why they call it a powerful rule. Okay, you have heard of this rule before as well, and that rule is called the octet rule. Okay, so octet rule says that in a stable molecule, each element has 8 electrons. Okay, that's what a octet rule means. Okay, so that's basically the full valence shell. All right. So, however, I want to mention this right now. Even though, we call this a powerful rule, it's one of the lamest rules. Okay. The reason is only, strictly speaking, there's only 4 elements in the periodic table. Almost all, not almost, always follow this rule. And those 4 elements are carbon, nitrogen, oxygen, and fluorine. All the other elements can violate this octet rule if they have to. We don't make them. We actually, it's basically we who do. Who do that. Okay, so we will not violate the octet rule for the elements. Unless we really have to. But okay, but those other elements, other than carbon, nitrogen, oxygen, and fluorine, can violate the octet rule. Okay, I just want to mention that. So, do we have any questions, concerns, comments? Now, why did I talk about this? The next step, so this is basically the beginning of Unit 2, Module 3. Okay, what we do mainly in Unit 2, Module 3 is drawing Lewis structures. I know that most of us have drawn them, but if you haven't, that's okay. By the way, how many of you have drawn Lewis structures before? Can I see the hands? Yeah, I see a lot of hands going up. How many of you haven't drawn Lewis structures before? Can I see those hands? That's totally fine. All right, we're going to start from the beginning and we're going to learn how to draw Lewis structures today. Okay, again, get this. The holy grail of drawing Lewis structures is the octet. Okay, so what we try to do is to have 8 electrons around all the elements in the Lewis structure. In the structure. Okay, that's going to be the goal. All right. Keeping that in mind, let me actually show the rest of the slide as well. So it says that to keep the atom happy, we need to have 8 electrons in the valence shell. All right. Anyway, so let's see if we can draw the Lewis structure of carbon dioxide. Let's start with this. Here we go.
6 valence, we need 2 more.
All right. So I've seen your structures on your whiteboards. Most of you, have a good structure for carbon dioxide. Okay. So just to bring everybody to the same page, Jack, did you draw a structure? Did you draw something? Okay. Okay. All right. So just to bring everybody to the same page, I'm gonna show you the way I think about this, way I approach this. And then I have some steps that I follow. If you follow those steps, you can. I can assure you that you're gonna get questions on the exam in the upcoming exam, right? All right. All right. So the first thing you do when you are asked to draw a Lewis structure for a compound is to count the valence electrons. Okay. So number one is to count the valence electrons. So carbon, how many valence electrons does carbon have? How many? Everybody? Thank you. 4. How do we know? Carbon is in the 4th group in the periodic table. Okay. So that means they have 4 valence electrons. All right. So, or you just write out the electron configuration of carbon. Let me do this. Okay. It should be 1s2, 2s2, 2p2. So in the valence shell, the outermost shell, you have 2 plus 2, 4 electrons. And that's how we know the number of valence electrons of that element. Anyway, so carbon has 4 valence electrons. Oxygen has how many valence electrons? Everybody. Thank you. 6. And you have 2 of them. Therefore, 2 times 6 is 12. Altogether, we have 16 valence electrons. That is going to make 8 electron pairs. So what did I do here? I divided 16 by 2 to determine number of pairs of electrons I can have. That's we know because it's easier to distribute pairs of electrons rather than individual electrons. All right, that's the first step. Okay, counting the valence electrons. And the second step is to draw the skeleton of the molecule. All right, so we are familiar with skeleton because it's the Halloween time, so skeletons are everywhere. All right, anyway, so what do I mean by this? So we need to connect the atoms in our molecule. Whenever we do that, we always have the atom with the higher bonding capacity in the center. Between carbon and oxygen, which atom has a higher bonding capacity? Come there again. Thank you. It's carbon, right? Carbon has a bonding capacity of 4. Why? It is 4 groups away from the noble gases. Okay, noble gas is 0, next group 1, next group 2, next group 3, and the carbon group is 4. So carbon is going to form 4 bonds. And then on the other hand, oxygen form how many bonds usually? Thank you, 2 bonds. Okay, so between carbon and oxygen, carbon has a higher bonding capacity. Thus, it goes in the center. Okay, and to that, I'm going to have 2 oxygen atoms bonded like this. Right, that's my step 2. I just drew the skeleton. Right, in step 3, I am going to distribute my electron pairs starting with the outer atoms. I have 8 electron pairs. I already used 2 of them as bonding electron pairs to connect carbon and oxygen. By the way, one of these lines indicate a bond, okay, a single bond. Okay, each bond has 2 electrons in it, so that's an electron pair. So I have 8 electron pairs. I use 2 of them, 1 and 2. So I'm left with 6 more. So I'm going to distribute them starting with the outer atom. So 1, 2, 3, 4, 5, 6, 7, 8. Right? And when I do that, I say that I have 1, 2, 3, 4 electron pairs around oxygen, meaning how many electrons? 4 electron pairs means how many electrons? 8 electrons, thus the octet around the oxygen. Okay, and same thing with the other oxygen. Like if you count the number of electrons, electron pairs, we have 1, 2, 3, 4 electron pairs, meaning 8 electrons. But around carbon, how many electrons do we have? Come there again, Tyler. We only have 4 because we only have 2 bonds or 2 bonding electron pairs. Therefore, we only have 4 electrons. Therefore, carbon does not have an octet. So in a situation like this, what do? We delocalize the lone pairs from these terminal atoms with this carbon atom. So delocalize means you're making a double bond now, right? So you delocalized to make a bond with the central atom. If you do that, okay, you're gonna get carbon double bonded to oxygen. Now oxygen only has 2 electron pairs like this. We're gonna name them in a second, okay? And then on the other side also, I'm gonna have oxygen with just 2 lone pairs. Okay. Now this carbon has 1, 2, 3, 4 bonding electron pairs around it. 4 pairs means 8 electrons. Carbon has an octet. And when it comes to oxygen, we have 1, 2, 3, 4 electron pairs around it. So 4 electron pairs means 8 electrons. Therefore, oxygen has an octet as well. Therefore, all of them have octets. So that's going to be my Lewis structure for carbon dioxide. All right. What questions, concerns, comments do we have? Again, the holy grail is the octet. Each atom must have an octet of electrons in the valence shell. I want to mention one other thing while we're looking at this. This is just, getting the naming down. Okay. So let me redraw the carbon dioxide molecule. All right. Here's my carbon dioxide. All right. Here's a question for you. I need a different pen. Maybe I have. Okay. Here we go. All right. So these electron pairs have a special name. Does anybody know what we call them? What do we call this? Anybody? We call them, yes, thank you, miss. What's the name, miss?
Lone pairs.
Thank you. Lone pair. What's the name, miss?
Marissa.
Marissa? Marissa, thank you, Marissa. Absolutely, yes. These are called lone electron pairs or lone pairs. Okay? And then, now you see that you have two lines here. If you have two lines, what kind of a bond are we representing here? Anybody? Thank you. This is called a double bond. Okay? Double bond. All right? So on the other hand, let me show you something else as well. Let's say that we have H2O, okay, which is going to look something like this. All right? So H2O has a single bond. This is a single bond. Okay? So we know how to identify lone electron pairs. We know what a single bond, a double bond, even a triple bond means three lines is triple bond means as well. All right. So again, if you follow the steps, chances are you're going to get this right. Okay. You have a higher probability of getting these questions right when you follow the steps. All right. Number one, count in the valence electrons. Carbon, 4 valence electrons. Oxygen, 6 valence electrons. Chlorine, 7 valence electrons, but you have 2 of them. 2 times 7 is 14. Altogether, 14 plus 6 is 20. 20 plus 4 is 24. We have 24 electrons, meaning 12 electron pairs. Number one. That's the first thing. And then I draw the skeleton of the molecule. Out of all these elements, carbon has the highest bonding capacity of 4. So carbon goes in the center. To that, I'm going to have 1 oxygen and then 2 chlorines bonded. Okay, that's my second step, drawing the skeleton of the molecule. And then I'm going to start distributing my electrons, okay, starting with the outer atoms. I have 12 electron pairs. I have used 1, 2, 3 here, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I distributed my 12 electron pairs among the atoms now. Now I see my oxygen has 1, 2, 3 lone pairs and then 1 bonding electron pair. A single bond is a bonding electron pair, meaning 4 electron pairs around it, meaning 8 electrons. And then when it comes to chlorine, I have 1, 2, 3 lone pairs and then 1 single bond, meaning 4 electron pairs, 8 electrons around them. So my chlorines and oxygens have octets of electrons. But carbon, on the other hand, only has 3 bonds around it or 3 bonding electron pairs, meaning only 6 electrons. So what do? We delocalize, because delocalizing is stabilizing. All right. And when we delocalize, we're going to delocalize from oxygen, not from chlorine. Okay. And when that happens, I'm going to get a double bond between oxygen and carbon. And one of these lone pairs is delocalized between the two atoms now. And then the other chlorine bonded to carbon remain intact. All right. Therefore, this should be my Lewis structure for COCl2. All right. What questions, concerns, comments do we have? Anything? Yes, I have a question over there. What's the name, Miss? Alexa, take the microphone, Alexa.
How does oxygen have the 6 in there? I thought it was 2.
Give me a second. If I understand your question correctly, Alexa, how does oxygen have 6 valence electrons?
Hmm.
All right. So the question is, how do we know oxygen has 6 valence electrons? If you write the electron configuration of oxygen is 1s2, 2s2, 2p4. So in the valence shell, which is the second shell, we have 4 plus 2, 6 electrons. Therefore, oxygen has 6 valence electrons. Yeah? Yeah. Another way to do that is, if I can have attention for 30 seconds. Right, if we go to a periodic table, right, I like this one. Where is it? This one. This. All right. So this is my D elements or transition elements. I'm going to skip them. Okay. These are my S and these are my P. So this group over here is termed 1A. 1. This is 2. This is 3. This is 4. This is 5. Group 5. Group 6. Group 7. Some periodic tables already have this. And this is 8. Okay. This number of the group tells us how many valence electrons it has. So oxygen, sulfur, selenium, tellurium, these are group 6 elements, meaning they have 6 valence electrons. That's another way to remember that. Alexa? Yeah, that's another way. Okay, or write the electron configuration. All right. What questions, concerns, comments do we have at this moment? Any other questions, concerns, comments? Yes, Robert, go ahead. Can I have the microphone with Robert, please?
Oh, okay, there we go.
Yes. Oh, good question. I like it. So how do we know that the double bond is made with oxygen, not chlorine? Okay. So here's the thing. Chlorine usually form only one bond. So I'm going to try to stick with that because common bonding capacity of chlorine is 1. On the other hand, oxygen usually form 2 bonds. Therefore, if I have to make a double bond, I'm going to give the preference to oxygen compared to chlorine between them. Yeah? All right. Any other questions, concerns, comments? All right. So with that, the question was asking about the number of double bonds, single bonds, and then the lone electron pairs. So let's count. Okay. So this molecule has 1 double bond, 2 single bonds, and then lone pairs we have 1, 2, 3, 4, 5, 6, 7, 8. 8 lone pairs, is that right? I think it's 8 lone pairs. All right, so that should be your answer. 1 double bond, 2 single bonds, and 8 lone. William, go ahead. Oh, okay. Yes, will help you out. All right, so with that, yeah, Sophia, go ahead. Sophia, give me a second. I'm gonna let me go to the next question, and then I'll come to you. Okay. All right, I'll give you 1 more minute. Please submit your answers on Top Hat. Oh, so I just saw it. Okay, so it talks about electron domains. All right, let me mention that so that there's no confusion. So what is meant by electron domains? Let me see. Okay. So an electron domain, Okay. So a lone pair, electron domain can be a lone pair. Okay. A single bond, a double bond, or a triple bond, or even a quadruple bond. So there are quadruple bonds also. But anyway, so if you have a lone pair, a single bond, a double bond, a triple bond, okay, those are considered as electron domains. Okay. For example, around the carbon or the central atom here, we have a double bond and then two single bonds, meaning we have three electron domains around this carbon atom over here. Okay, so in this example, but in your example, you have something else now. All right, I'll give you 30 more seconds. Go ahead. CF4, I'm going to directly draw because most of you already did. Okay, so it looks like this. So we have carbon, we have fluorine, another fluorine, another fluorine, another fluorine. Okay, so and then each of these fluorine has three lone pairs. Great. All right. What questions, concerns, comments do we have? Anything? Any questions, concerns, comments? Yes, I have a question over there. What's the name, miss? I'm sorry. Can you pay attention, please? Is it switched on? Yeah. Can you shout, miss, for a second? Yes. Can you go ahead? Electron domain and the bonding electron pairs around the central atom, they're the same. Okay, so if you have like four single bonds, you have four bonding electron pairs. So we have four electron domains around it. Yeah, the same. Any other questions, concerns, comments? Yes. What's the name is one more time?
Delaney,
Delaney, go ahead.
why is there a triangle? in
Oh, I see. Okay, I'm sorry about that. So, you don't have to draw them, okay? So this is me trying to draw a 3D molecule in a 2D plane. So a wedge like that means, like this means that bond is coming at you from the plane. If you have a dashed line on the other hand, they mean that that bond is going away from you into the plane. If you have like normal lines like this, they mean those bonds are on the plane itself. Okay, so if you draw the same molecule like this, I'm okay with that for now. All right. So you can draw that like this. That's okay. But if you see wedges and dashed lines somewhere in textbooks or online or somewhere else, what they means is that if you have a triangle or a wedge like that, that is a bond coming at you from the plane. If you have a dashed line, that is a bond going away from you into the plane. And if you have like normal lines like this, they are bonds on the plane itself. Yeah? No. I just want you to be able to, acknowledge them. That's it. All right. So with that, oops, what's going on here? So when you see molecular formula presented to you like this, okay, this has more information than when you have the same formula like this. For example, the same formula can be given to you like C2, H6, NO. Okay, this just tells us how many carbon, hydrogen, and oxygen atoms do we have in this molecule. But in this chemical formula, it shows you what atom is bonded to what as well. Okay, what do I mean by that? I'm going to draw this in my notebook now. Okay, let me go back to this. So if you have the chemical formula given to you like this, what this means is we have this carbon over here first. To that carbon, we have 3 hydrogen bonded. 1, 2, 3. And that carbon is bonded to another carbon atom over here. And that carbon has 2 hydrogen bonded to it. Yes. And that carbon is bonded to an oxygen. And that oxygen is bonded to a hydrogen. Okay. That's what it means. And also, when you are making the Lewis structure, you need to keep in mind, you need to show octet of electrons. Okay. So these carbons have octets of electrons because you have 4 bonds around them. But this oxygen over here has only 2 bonds, meaning you need to have 2 lone pairs to make this oxygen have an octet of electrons as well. Okay, so this should be the Lewis structure of this molecule. Do I have a question over there? I saw. Actually, did we have a question? Are we okay? Okay, perfect. Okay. All right. Yes, miss. Can I have the microphone here, please?
Wait, so why are the
Does it matter where you draw the lone pairs like on?
No, yeah, it doesn't matter. I understand your question. You can draw the lone pairs on top of them, at the bottom, or one at the top, one at the bottom. It's fine, as long as you have 2 lone pairs to fulfill the octet. All right. Now, here's the main thing I want to do here actually. So this same structure can be represented like this. Instead of drawing my carbons and hydrogen bonded to carbon, I can write this. I can draw this.
What was the balance in
Okay. And I'm going to call this the line structure of the same molecule.
As for load?
Line structure. This is the Lewis structure. Okay. Here's what I want you to do. On top pad, I want you to let me know. All right. And then here are our responses. Okay. So when we build line structures from Lewis structures, okay, the carbon atoms are represented by ends and bands. And hydrogen bonded to carbons are implied. You don't have to draw them explicitly. They are implied. They are there to fulfill the common bonding pattern of carbon. For example, not an example, carbon usually forms 4 bonds. Okay. If you only have 2 bonds on that carbon, you're going to add 2 carbon hydrogen bonds to make that carbon has 4 bonds, have 4 bonds. And then hydrogen bonded to atoms other than carbon are always explicit, meaning you need to draw them out. For example, in our case, we had to draw the hydrogen bonded to oxygen. Okay, that is not implied. That should be explicit. And all the other elements except for carbon atoms and hydrogen bonded to carbon are always explicit, meaning these other elements like oxygen, if they have fluorine or nitrogen or any other elements than carbon or hydrogen bonded to that carbon, you need to write them out. Okay. So those are the rules we can make, we can use to draw line structures. I'm going to do one other thing here. I'm going to show you how to convert a line structure to a Lewis structure very easily. Okay. So here's I'm going to redraw this line structure. Okay. Here's my line structure. Okay. So here are the rules again. Okay. My ends are carbon. Here's an end. It is a carbon. Here's a band. That is a carbon. And then we have an oxygen here, hydrogen here. And then this carbon over here has only 1 bond. Therefore, I need to add 3 carbon hydrogen bond to make that carbon have 4 bonds. And this carbon, on the other hand, has 2 bonds. Therefore, I need to add 2 carbon hydrogen bonds to make it have 4 bonds around it. Okay. And then the only other thing I want to do is I want to make sure that all my elements have an octet of electrons. This oxygen line structure to a Lewis structure. Right? So you should be able to go from line to Lewis or Lewis to line easily like that. That's it. All right. What questions, concerns, comments do we have at this moment? Yes, sir. Can you shout? Because microphone doesn't seem to be working over there. Can you shout, sir? Yes.
How can we write CH4 in line structure if
We don't write a line structure for CH4
okay
because we only write, draw line structures to make our life easier. Okay, not the other way around. CH4 has only one carbon, therefore we don't draw Lewis structures for that, line structures for that. Okay, we draw line structures only when we have more than more than one carbon, and hydrogen bonded to them. Yeah. All right. Any other questions, concerns, comments? Okay. So with that, let's have some fun with this. One. All right. So before I get to answers, I'm going to show you the way I would handle this. All right. So even in an exam or anywhere, even in the exam paper itself, you can draw convert this to a Lewis structure. How do we do it? I know my ends are carbon atoms. Here's an end. That's a carbon. I want to take a pencil. I'm sorry. Give me a second. Right. So here's an end. That's a carbon. Here's another end, another carbon, another end, another carbon. My bends are carbon too. Here's a bend. It's a carbon, 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 and carbon. And then the common bonding pattern of carbon is fulfilled by carbon-hydrogen bond. This carbon has only one bond. Therefore, I need 3 carbon-hydrogen bonds for this. And then the same thing here. I'm going to need 3 carbon-hydrogen bonds to make this carbon have 4 bonds. Okay. Same thing over here. I'm going to need 3 carbon-hydrogen bonds to make this have 4 bonds. This carbon here has 3 bonds already. Therefore, I just need 1 carbon-hydrogen bond. This carbon over here has 1, 2, 3, 4 bonds. Okay. I'm not going to change anything there. Same thing with this, and this as well. So we are done with that. Okay. Now, at this point, this is still not a Lewis structure, but this is good enough for me to determine the chemical formula. So I'm going to start counting. So first, the carbon atoms, okay, then hydrogen, then I have nitrogen, and then oxygen. All right, carbons. I have 1, 2, 3, 4, 5, 6, 7, 8. Please let me know if I make a mistake. 8 carbon atoms. Then hydrogens, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. And then nitrogens, I have 1, 2, 3, 4 nitrogens. In oxygens, I have 2 of them. Here we go. So this should be my chemical formula for this structure. All right. What questions, concerns, comments do we have? Anything? Any questions, concerns, comments at this point? All right. So you're gonna see, these are the easiest questions you can get. So everybody should get 100% on questions like this. Okay. You just need to make sure that you replace ends and benzene with carbon and add carbon hydrogen bonds and count them properly. Okay. That's it. Any questions? So if that is the case, I'm going to open the first question I opened today at the beginning of the class. Here you go. I see that I have more than 90% answers, but I hope that everybody got a chance to revise the answers if they had to. I'm going to close this question in 5, 4, 3, 2, and 1. All right. Okay. Now, before I look at your answers, okay, here's what we need to do. We need to make sure when we make this structure a Lewis structure, we need to make sure that we include the lone pairs to have octets around all the elements except for hydrogen. Okay. So oxygen over here has only 2 bonds, meaning two electron pairs, meaning 4 electrons. So we need 4 more electrons. So what do? I'm going to add 2 lone pairs, make it have octet of electrons. Same thing this with oxygen as well. Okay. Then I have the nitrogens. These nitrogens have 3 bonds around them, meaning 6 electrons. Therefore, I'm going to need 2 more electrons to make it have an octet. Therefore, I'm going to add 1 lone pair to this nitrogen, and even this nitrogen. Okay. And then even this nitrogen, we have 1, 2, 3 bonds around it, meaning 6 electrons. Therefore, I need to add 2 more electrons. Therefore, I need to add 1 more lone pair. Okay. Then I count them. I have 1, 2, 3, 4, 5, 6, 7, 8 lone pair electrons. Okay. That's it. Done. Yeah. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Okay. I believe that's the correct answer. Let's see if Top Hat agrees. So initially we had a good variation of the answers, but here, yeah, we are converging on 8, most of us at least. Right, there are some other answers as well, but I'll reopen the question. All right. Any questions, concerns, comments at this point? So we learned how to draw, we learned how to draw Lewis structures today. We learned how to draw line structures. We learned how to convert line to Lewis structures. And then we emphasized the importance of the octet of electrons around each element except for hydrogen, okay, when you draw Lewis structures. So with that, let's have some more fun now, okay? So I'm done with the objectives of today's lesson. All we had to do is to, let's see. Let's do this. Yeah, let's draw the Lewis structure of ozone. By the way, ozone is not a cyclic structure, meaning they are not, connected to each other to make a cycle. Okay, so it's not that. Can we draw the Lewis structure of ozone? With the steps, right? You're gonna get this right very easily. But if you try to do something else, I mean, your brain can take you to different places where you don't want to be. All right, it happens. Okay. Anyway, so ozone, O3. Oxygen has 6 valence electrons. When we have 3 of them, 3 times 6, it's going to bring us 18 electrons because 3 times 6 is 18, right? Okay. 18 electrons. That means we have 9 electron pairs. Okay. So central atom has to be an oxygen atom. So I'm going to have oxygen. And to that, I'm going to have 2 other oxygen atoms bonded like that. Okay. I have 9 electron pairs. I'm going to start distributing them, starting with the outer atoms. Okay. 1, 2, 3, 4, 5, 6, 7, 8. The 9th one should go in the oxygen in the middle. Okay. Now I see that my oxygens at the terminals, okay, have 8 electrons because 3 lone pairs and 1 bonding electron pair mean 4 electron pairs, meaning 8 electrons. But oxygen in the center have only 1, 2, 3 electron pairs, 1 lone pair and then 2 single bonds, meaning only 6 electrons. Okay. So what do we do now? We delocalize. But here's the thing. We can either delocalize from this side, this is option 1, or from this side, option 2. So there are 2 options for our Lewis structure. We can have a double bond on the left-hand side if option 1 happens, okay, giving rise to this Lewis structure, or if the option 2 happens, then we're gonna have our double bond on the right hand side, like this. Okay, so we can say that we can draw two Lewis structures for the same chemical formula. Whenever that happens, we say that our molecule shows what we call resonance. Okay, as a result of that, these structures are known as resonance structures. Okay. Whenever we have a molecule that shows resonance, the actual structure or the experimental structure is not this, but a hybrid of both of them. Okay. So in the hybrid structure, get this, the bond on the left-hand side is not a double bond, not a single bond, but a bond between a double and a single bond. So I'm going to indicate that by a solid line and a dashed line like this. Okay. And then on the other side, again, my bond on the right-hand side is not a single bond, not a double bond, a bond between a single and a double bond. I'm going to indicate that by a solid and a dashed line like this. Okay. And this is known as the hybrid structure of this molecule. And no, you do not write lone pairs, draw lone pairs in the hybrid structure. That is not an accident. That's not a mistake. You do not draw lone pairs in the hybrid structure. All right. Any questions, concerns, comments? I'm going to write one other thing if I have time. Can I? Yeah, I have. Give me like 30 seconds. I just need 30 seconds. Okay. Now, here's something to appreciate, everybody. Okay. So when a bond is formed, electrons are delocalized between two atoms. But when you have resonance, these electrons are delocalized between more than two atoms. Okay. I call this extended delocalization of bonding electrons, due to resonance. Okay. And what does it do? It decreases the potential energy. We talked about why. It also decreases the kinetic energy because it has more space. Electrons have more space. They slow down. As a result of that, the total energy goes down as well. Okay. Because the total energy goes down, we say that this is going to increase the stability of the molecule. So resonance is stabilizing, and this is why it is stabilizing. All right, I think with that, I need to give you the attendance code for today. Right, when we come back, so this is done. This is all you're going to see on the test as well. You had two reviews posted on D2L. Have fun with them, and when we come back on Thursday, we will have more fun with our review session. Here we go. Here's the attendance code. All right, bye everybody.